Radioactivity is a natural component of our environment. This is not something that man has done to our planet. It has always been here. Radioactive elements are natural. Humans and other living organisms are adapted to survive in a normal exposure to radiation. There's radiation that comes from outer space that gets through the atmosphere, small quantities, but it does matter, radiation from outer space. And there's also radiation that comes from radioactive elements that are present in the Earth's crust. All of the elements beyond atomic number 83, which is bismuth, everything larger than bismuth is unstable and radioactive. So if you look at the periodic table, after bismuth, you see the atomic masses are all in parentheses because they're unstable. There are also certain isotopes of the smaller elements that are radioactive. Like carbon has 2 isotopes that are not radioactive and 1 that is radioactive. Well, these radioactive nuclides decay at different rates. Some decay very quickly, some decay extremely slowly. And the way we measure that is with a concept called half-life. The half-life is how long it takes for half of the parent nuclides to decay to the daughter nuclides. So if you have one half-life, after one half-life, half of the sample has decayed. But that does not mean that in a second half-life, you'll have nothing left. In the second half-life, it's another half. It's just getting cut in half every time. So after one half-life, you have 1/2 left. After 2 half-lives, you've got 1/4 left, a half of a half. After 3 half-lives, you have 1/8 of what you started with. It's a half of a quarter. Some nuclides decay very quickly. They're said to be very active. They have many decay events per unit of time. And a decay event is the emission of radiation by a single radioactive nuclide. So one atom emitting radiation, that is one event. An active radioactive compound will have that happen a lot. Radon-220 has a half-life of approximately 1 minute. That means that after 1 minute, half of the radon-220s have decayed. So if you start with 1 million radon-220 atoms, after 1 minute, you've got 500,000 left. After another minute, you have 250,000 left. And the radon is going, you know, there were so many mistakes in this chapter in the book. I think this is supposed to be radon-220. In the online version of the book, they actually have just completely the wrong equation in here. So this should be radon-220 atoms. So there's 250,000 left. If you wait another minute, you'll have 1/8 of a million. Another minute, 1/16 of a million. It's just cut in half every time. So a half-life of 1 minute, that's pretty short. Thorium-220, thorium-220 is much less active. Let's look at that one. It has a half-life of 14 billion years. That's a little different from a minute. So if you started with 1 million thorium atoms, it would take 14 billion years to cut that in half. For radon-220, it's 1 minute. So here we have a graph showing what's happening here. So each of these little balls represents 1/10 of a million. So we're starting at 0 years with 10 of these. After 14 billion years, we've got 5 left. After another 14 billion years, we have 2.5. After another 14 billion years, we have 1 1/4. and it gets just cut in half, cut in half, cut in half. The half-life of a radioactive nuclide is not affected at all by physical conditions. If you heat it up, if you cool it down, if you put pressure on it, there's nothing you can do to it that's going to change it. It's going to decay when it decays, and that's it. Here's just a table showing some different half-lives for different nuclides. So, there's thorium-232, 1.4 times 10 to the 10th years, that's 14 billion. Here's carbon-14, 5,730 years. Radon-220, just under a minute, 55.6 seconds. And thorium-219, 1.05 times 10 to the minus 6 seconds. And that undergoes alpha decay. So we've got a bunch of alpha decays, and this is a beta decay. Just for your information. Okay, let's look at this question. A radium-226 sample initially contains 0.112 moles. How much radium-226 is left in the sample after 6,400 years? The half-life is 1,600 years. So we're only going to be looking at very simple problems. There's much more fancy ways to solve these, but we're going to look at these in a very simple way. So here's our time, 6,400 years. What we need to know is, how many half-lives is that? Well, what if we take 6,400 and divide it by 16? That'll tell us how many half-lives. So 6,400 divided by 1,600. And that's what, 4. So 4 half-lives. Which means it's going to get cut in half 4 times. So we've got 0.112. After 1 half-life, I got my calculator out, didn't take off the cover. 0.112, it's going to get cut in half, divide by 2, 0.056. After another half-life, divide by 2, 0.028. Another half-life, divide by 2 again, 0.014, and one more, 0.007. So there's 1, 2, 3, 4 half-lives. So the answer is 0.007 moles. Yeah. The goal of a question like this is, do you understand the concept? Not can you do crazy math with exponents, but do you understand the idea? It gets cut in half with every half-life. Naturally radioactive elements either have very long half-lives, which is why they're still around, because it takes them a long time to decompose, or they're continually being formed by some other process. Uranium has a long half-life. The thorium had a really long half-life. When it decays, it creates another element that's radioactive. So we've got some that are being created and some that just take a really, really long time. Uranium is the heaviest of the naturally occurring elements. It's atomic number 92. Uranium-238 decays to thorium-234. That half-life is 4.47 billion years. That's why there's still uranium-238 around. So whatever we started with on the planet has been decaying this whole time. But because it takes 4.47 billion years for half of it to go away, it's still around. It makes thorium-234. Thorium-234 is radioactive. That decays to proactinium-234. That has a half-life of 24.1 days. So that's not being created very fast. It's decomposing fairly quickly, but it is continually being created. And the proactinium is also radioactive, and that decays to uranium-234. That has a half-life of 244,500 years. Really long. So there's going to be a fair amount of that proactinium-234 around because it takes a long time for it to decay. And it goes through several more steps like this, just changing from one nuclide to another, and they're all radioactive. And it keeps going. It includes the formation of radon gas, and eventually gets to be lead-206, which is not radioactive. And there it stops. So we have all of the uranium-238 in the environment is slowly decaying to lead-206. And eventually it'll all be gone, but how many billions and billions of years is that going to take? All of the nuclides in this decay series are going to be present. And how much of them there are depends on how long their half-lives are. So things with longer half-lives there's going to be more of it around than things with short half-lives. Here's a graph that shows this decay series of uranium-238. So it's thorium-234, proactinium, uranium, then thorium, radium, radon, polonium, and it goes through all these things, and eventually it ends up as lead-206. You don't have to remember any of that, but just that's what happens when things decay. They form other things, and a lot of times those other things are also radioactive.